Yeah. Okay, so we'll start part 2 now. We just finished talking about ventilation loads, and now we're going to move into a review of the space conditioning loads. So again, this should look familiar. It should be a review from previous lectures. In the last slide, we were talking only about the cost of only ventilation. So now we want to talk about, okay, well, what about just maintaining the space temperature at a comfortable temp? So you'll remember that these are from previous lecture. When it's cold outside, we've got some heat coming in from solar gain. We've got heat that's leaving through conduction and convection and basically our transmission losses. Okay, we've got infiltration losses or exfiltration losses, either way. And then we've got our HVAC system trying to add heat to the space to maintain this temp. And we've got the internal gains of appliances and people and pets and things like that. Okay, but in net we need all the energy coming in, okay, to add up to equal the energy going out if we're going to maintain a constant temp in here. In the warmer periods of the year, we still have some solar gain. We have now our transmission heat transfer is going the opposite direction. Okay, it's warmer outside than it is in the building, so our heat now is moving through the envelope to the inside of the building. We've got infiltration that's actually bringing heat into the building potentially. We've still got our internal gains, but now our HVAC system, instead of generating heat like it did over here, needs to take heat out of the building. So it might be air conditioning. Or if we don't have this, what do we know happens? By 3 o'clock in the afternoon, your house is quite a bit warmer than the 70 degrees you'd like it to be, right? So, okay. So again, this is just in very simple terms. If there's more heat coming in than there is leaving, the temp's going to rise. If there's more heat leaving than there is coming in, the temp is going to drop. And if you want to maintain a constant temperature, you've got to equalize those. So that's the purpose of the HVAC system from a space conditioning point of view with regard to temperature alone. Okay. So how do these systems add or remove heat from the building? We've talked about before how we generally need some kind of a heat transfer medium, and usually that's air or water, or if not water, it's some water-based liquid like a glycol water solution or something, right? We need some medium to be able to move the heat around, okay? To move it from the place where we add the heat, like in a furnace or a boiler, to the place where we want that heat to go, like a bedroom, okay? In general terms, we can utilize any of the 3 modes of heat transfer: conduction, convection, radiation. Okay, so radiation, we know we have certain heating systems, and actually there are some cooling systems that are kind of relatively new to the commercial world that use kind of radiative cooling, if you will. But in the residential world, we tend to think of radiant floor, hot water or electric baseboard, or radiant panel radiators, or the old style steam radiators, whatever. So a lot of radiant heating. Conduction, that happens sort of in the midst of the process, like where we have a heat exchanger or a coil, and then convection similarly, like at a coil or in a heat exchanger in a furnace or whatever. So all these modes are happening throughout the system to get that heat to move around, and so we can try to control it and put it where we want it. Okay, systems are generally groups of interacting subsystems. So it's all, you can draw a line around almost anything and call it a system, right? And the system is defined by that boundary that you draw. Okay, so the furnace by itself is a system. There are systems within the furnace. The burner and heat exchanger is a system within the furnace that's separate from the blower, right? The furnace, if you want to draw the boundary bigger, the furnace with all of its associated ductwork and diffusers and return grills is a system. Okay? The whole house is a system. So, it's all about where you draw your boundary. So, here's an example. We generate heat at a boiler. We transfer that heat to some water that's in the pipes that's circulating. Okay? We pump that water to another part of the building. The hot water flows through a radiator and transfers the heat to the space. Okay? The hot water flows to a coil in an air handler where ventilation air moves over the coil and the ventilation air is heated before being delivered to the space. The subsystems there we've got a boiler, we've got pumps, we've got piping, we've got radiators, we've got the coil and the air handler, we've got the air handler itself. There are all these systems within the greater system, which is, if the greater system is all the HVAC in the building, these are all subsystems. Okay, each subsystem has its own efficiency characteristics, right? The boiler has some associated AFUE or other efficiency metric. The pumps have some, say, efficacy GPM per or GPM per watt kind of thing, right? Or just a pump efficiency, 65%, whatever. The piping, we don't generally quantify it, but we know that if we undersize the piping, then the pump has to do a lot more work. And the radiators have some heat transfer efficiency, right? So there are efficiencies for all these different things. So how can you possibly quantify the efficiency of the whole system? Right? Well, you can, it takes some work. But what you have to remember is that you've got to look at individual efficiencies of different subsystems and kind of figure out how it all fits together and what is going to be your method for determining an overall efficiency. Or you let the building run and you take really high level macro scale measurements of how much natural gas and electricity is coming into through the meters, and how much actual heating is happening or cooling is happening in the building. That would be the total system efficiency. Yeah. Okay. So as I said in my intro here, there are just so many different HVAC systems out there. It's like can't possibly list them all or cover them all here. So we're just going to focus on a few. It's also difficult to organize or categorize them. There are a lot of options. You can categorize them based on, okay, do they provide ventilation, heating, or cooling? You could categorize them like within any of these categories based on what kind of heat transfer media. So let's say it's a heating system. Okay, is the heat transfer medium air or water? So that further would break this category into more subcategories. You can look at what kind of fuel. Okay, is it electric, natural gas, coal, oil, solar? What kind of system is it with regard to the fuel source? Does it have heat recovery or not? Is it a central system, like a plant system, what we often call plant systems, or is it some more distributed central system? Or is it a zone level system? Okay, so is it the main one boiler in the building, or is it all the panel? Is it like one of several air handlers that have hot water coils in them, or is it individual radiators out in in each room? What kind of system are we talking about? Okay, so here's one attempt at kind of listing out some different systems and categorizing them, right? So over here in this table, you've got all air side systems, where air is the heat transfer medium. Here you've got all what we call wet side systems, or hydronic systems, where some kind of water-based fluid is the heat transfer medium. You've got refrigerant systems. You've got systems that are central or plant systems, and you've got all electric systems. There's some overlap here, so you'll see that a boiler is a central plant system that's also a wet side system. I could have put boiler up here, right? So there's definitely some overlap, and then you can kind of like start to categorize them also in terms of, do they provide ventilation, or heating, or cooling, or all three, or two of the three, right? Or in some cases where I put a 0/X, it can provide ventilation, but it doesn't always, right? So if we look at a furnace in the residential, just like we talked about a little bit ago, the convention, for the longest time in residential was, there is no active ventilation. You just let the house breathe, right, through the leaky envelope. Okay? And now we started to see where, okay, well, let's put a serious exhaust fan in there that runs a certain amount of time and let that pull outside air in for ventilation. But you could say, well, why don't we just take, we've got this furnace, it's got a blower in it, it's just recirculating inside air. Why don't we just put one little duct that goes off somewhere to an intake louver to outside air, and bring a certain amount of outside air into that airstream for the furnace, and let the furnace blower bring some fresh air in and mix it with that return air and heat it up and deliver it. Okay. You'll see that that's not necessarily a bad idea, but you want to take it a little further than that and decide how you can do that more efficiently, so that you're not always ventilating when sometimes the furnace needs to heat when there's nobody in the building. You don't really need the ventilation so much, right? So we're going to talk more about that on Friday.
Yeah.
But anyway, so that's why you see some of these have a 0/X, right?
So I'm not going to pick through these in too much detail, but hopefully most of these are familiar, and I try to include, don't forget that, you can have passive ventilation. You can't do that. And by that I don't mean a leaky envelope, I mean something a little bit more engineered, but that doesn't necessarily need a fan.
Like you said,
Breezeways, or, right, some kind of a ventilation chimney, something that can cause some natural passive ventilation, but you can also shut it off when you don't want it, or when it's, or neck it down when it's too cold, or somehow provide some way to have some heat exchange so that it doesn't come into the house screaming cold, But anyway, passive means are always good if you can figure them out. In the wet side system, for plant systems, I did include solar hot water, right? Anyway, so there are lots of different systems out there, and this is just a tiny fraction of what's really out there.
Really?
Okay.
Wow.
So,
Just a ballpark.
yeah. Okay, so with so many different systems, how do we ensure that we get high efficiency? Okay, so I'm going to try to provide some guidelines. So let's look at ventilation first. Okay, so you have to ventilate, but how can we do that efficiently? First of all, try to recover heat from outgoing exhaust air to incoming fresh air. And again, that's if you have incoming fresh air that you're controlling. If you just have an exhaust fan, no supply fan, you're kind of hosed on this one. Okay? Don't oversize or over-ventilate, and vice versa. So we don't want to oversize our ventilation system and over-ventilate because of the cost of heating and cooling that ventilation air. We don't want to under-ventilate because of the cost in terms of human comfort, health, right? Consider dynamic systems that can operate with varying ventilation rates to match the ventilation rate to changing requirements, such as occupancy. Okay? So the code says, based on your square footage and the number of bedrooms, you just need this 60 CFM all the time. Well, that's in the commercial world. We don't do that. We don't look at that simply.
Because you don't want to run it at midnight.
Yeah.
Or between
Why would
midnight
you?
and 6 in the morning.
Yeah. Why would you?
Right.
And so it's actually when Montana adopted that IECC 2012, they amended it in certain ways, and one of those amendments was to say, okay, we get this, continuous ventilation thing, but in this cold climate, we're going to let people ventilate, some fraction of the time. They just then have to increase the CFM for when they are ventilating. I don't think at this point, I don't think it goes far enough on the residential side to be able to sort of help guide people toward more sophisticated systems that would say, okay, when the building is at peak occupancy, we need this many CFM ventilation. When it's not occupied, we need something much less. And let's find a way to make a system that modulates between those extremes. Okay. And in the commercial world, we do that on the regular. It's not, even in the commercial world for a long time, that wasn't the norm. The norm was, and we'll cover this again more on Friday, but the norm was to just say, okay, the ventilation rate requirement for design occupancy is X, so we will make an air handler that can provide that much ventilation all the time. Right? It took a while even there to get to where we have modulating ventilation rate. But we might as well start thinking about that also in the commercial or in the residential world now. Select the highest possible fan efficiency or efficacy. Okay? So even if you're just comparing bathroom exhaust fans on the shelf at Home Depot, it's not that hard to look at how many CFM is it nominally rated to move, how many watts does it draw, take the ratio, do the same for the one next to it that says it's higher efficiency, see how much improvement you're getting, pick the more efficient one if you can afford it. Okay. Too often we walk in, we say, bathroom fan's a bathroom fan, pull the cheap one off the shelf and go, right?
Well, it sounds like a jet airplane.
Yeah.
Fired up.
Yeah, some do, especially if they're oversized. Right?
Yeah.
Okay. And in some cases, it might be better to decouple your ventilation system from your heating and cooling systems. Okay. So really what I'm getting to here is like, when I mentioned, okay, well maybe you want to just bring some outside air ducted into your furnace.
When it's not when you need to exchange, when there's occupancy.
Yeah. And that's what I'm getting at here is like, okay, well if you're going to bring outside air into your furnace, but you can't control how much and when, maybe you don't want to bring it in your furnace. Maybe you do want to keep these as two separate systems. Have one system that's just devoted to ventilation so that you can get the tightest control possible on that ventilation and make sure you're only ventilating as much as you need and you're doing your heat exchange or whatever. And a separate system that does the heating and cooling. Okay. Either way, You just got to be smart about it. But it's a good question to ask. Okay, do I want to try to couple those systems together, make it all one, or do I want to keep them separate?
Well, I guess that makes sense when you're in a climate that's one extreme or the other, either heating or cooling climate.
Yep. Okay. So let's see.
Is that becoming more standard also? Is to keep those two systems separate?
You know, it's hard to say in the residential world. I mean, it started out like when we started saying in the residential building, okay, we need ventilation that's somewhat active, controlled. The first step was, okay, well, let's just put more bathroom and kitchen fans, maybe tie them together into a central fan, whatever. Okay, that's decoupled. I mean, that's your ventilation there has nothing to do with your heating and cooling.
That's completely.
I mean, they interact. So
Okay.
when I say decoupled, I mean from a design sense. They certainly do interact with one another because how much ventilation you bring
That's
in.
what I
you
figured.
gotta
I figured
equal.
there'd be they'd be separate, but there would be a place where they would eventually rejoin and.
Yeah.
But in a residential, you're saying completely separate, where the bathroom fan is just.
The furnace doesn't know what the bathroom fan is doing and vice versa.
Right, and they're not in the same room.
They're not in the same room. They're not designed to have any controlled interaction.
Right, exactly. There's the buzzword.
Okay. So so let's look at this concept of decoupling. So if we provide a dedicated air side ventilation system separate from the systems that heat and cool, well, why would we do that? Okay, and it's to avoid this challenge of if you're trying to ventilate, heat, and cool with the same air side system. This is kind of specific to air side systems. The airflow rates that are required for cooling, heating, and ventilation are generally different. Okay, and the reason is that for cooling and heating, the temperature differentials are different. So again, remember that the heat, total heat energy, equal to 1.08 in the sensible heat, 1.08 times delta T times CFM. If you have, for a given amount of heat, Q, if you have a bigger delta T, you can get away with less CFM, and vice versa. Okay. In cooling, we have a smaller delta T than we do typically in heating. So a lot of heating systems, let's take an air side system, when it's heating, it might discharge air at 110 degrees. Okay. And it's trying to maintain, and the return air is coming back at 70. Okay, so it's got a 40-degree delta T.
Mm-hmm.
In a cooling system, it might discharge at its lowest, 55, right? We talked about that. Okay, and it's coming back at 70.
Mm-hmm.
Okay, so 15-degree delta T. So with less delta T on the cooling for a given load, I need more CFM.
Right.
So if you have a system that's a heating and cooling system, the CFM is typically going to be sized to be able to meet the peak cooling load. Okay, and then that means it's going to be a little higher than needed on the peak heating, which just means for something simple like a furnace that just cycles, it just means it'll have less runtime in heating. But both of those airflow rates are going to be a lot higher than what you need for your ventilation.
Right.
So if you just, without being real smart and designing some modulation into the system, if you just try to combine all these things into one, say, furnace with an air conditioner, you could end up over-ventilating if you don't do it in a careful way and engineered way. But also, just as we mentioned a minute ago, there are times when you need the ventilation but not the heating or cooling, or vice versa. And so, again, with a simple air side system that doesn't have a lot of modulating dampers and sophisticated controls, it's kind of all or nothing. It's like
Spring and fall in Montana,
right.
like a day like today. I mean, it's 65 degrees, 70 degrees out today. So
Right.
you don't really need to heat or cool, but you would definitely want
Right.
the extreme.
So just imagine, let's say you do the furnace idea. You take a little skinny duct that comes off the main return duct and goes to the outside. So you're bringing a small amount of outside air in to mix with your return air that goes into your furnace blower. Okay? And let's say it's one of those spring or fall days where, like you said, you don't need any heating, you don't need any cooling. Okay? To get that outside air in, you got to run the furnace blower.
Right.
The furnace blower might be moving several hundred CFM, or even like up to a couple thousand CFM for a home. And you're running that furnace blower to move a total of, let's say, 1,000 CFM, where only 60 of it is ventilation air. You don't really need to move that other 1,940 CFM.
See, and I did that for years.
Yeah, a lot of people do. They'll go to the thermostat, turn the furnace blower on to fan only, just to get some air circulation.
Absolutely.
And you might have been doing it when there wasn't even any fresh air incorporated, because most residential furnaces don't have an outside air intake.
I had intake.
You did?
Yeah.
Okay, yeah. Well, most of them don't. So you would have, in a lot of cases.
You could feel that, usually I'd do it when I wanted to draw in some cool air.
Yeah,
You know, like.
and you'd feel that.
Yeah, towards the end of the
Yeah.
evening when, you know, sun's down and it's starting to cool a little bit, the house is.
Yeah. And that could have been, in some, I don't know your scenario because I wasn't there. In some cases, you will still feel that cool air just because of the duct leakage coming in, the return duct from a basement or a crawl space or whatever, right?
So, but the point.
Point is, it was working. I mean, yeah, if it was cool, you
Oh,
had
no,
some
no,
outside
the point
air.
is that
It's a lot of air to move just to get a little bit of ventilation.
Exactly.
Yeah, yeah.
Okay.
Okay, so it's not to say that you couldn't do it with more controls and more hardware to make it happen more efficiently. But if you can't go there, you know, it might not be the best option. So here, just like I say here, if the system can't stop ventilating when heating or cooling an unoccupied building, then you'll end up ventilating when not needed. Also, you know, hydronic system efficiencies for heating or cooling might be higher for a given budget. So for your budget, you might be able to afford a higher efficiency of heating or cooling with a hydronic system instead of an air side system. So let your ventilation system be the only air side system because you can't ventilate with water.
Right.
Okay, but do your heating and cooling with water.
So a hydronic system's obviously still gonna have some sort of a, air handler or an exchange?
Not necessarily, right? So radiant floor or any kind of radiant only system
Mhm.
doesn't need an air handler.
But just.
But
just
still
some sort of
some kind of ventilation system,
Okay.
yeah. So, but now you downsize your air side to like one little tiny HRV or something like that, right?
Interesting. So sometimes, I guess I'm hearing that you can't always hope to buy one unit that's gonna do everything. You might have to buy several different components.
Yeah.
And try to coordinate them as best as
Yeah.
possible. And you'll get, even though the cost might be a little more upfront, the efficiency over time is gonna be much better.
Could be,
Okay.
yeah. Again, it's a complicated world and a lot of different
No,
systems to choose from.
it's-
But in the commercial world, we very often have one system.
Once
that does
again,
it
it's
all.
almost a little more counterintuitive, because a lot of folks would think, hey, you know, I've got this ERV or HRV that does everything.
Mhm.
You know, I mean, it's one-stop shop, I
Yeah.
can drop it in
Yeah.
and never have to worry about it again.
Well, in the residential world, it would be very rare to see an HRV that can handle the heating and cooling loads of the building. That would be a sizable air handler.
Hmm.
In the commercial world, we do see those, right? And you could do it in the residential world, but typically when you see HRVs these days in residential, which they're few and far between, because they're an expensive little piece of equipment that has not been the norm.
Hmm.
But when they're there, they're generally sized to handle only a ventilation requirement. And we have separate systems for the heating and cooling. But in some cases, you'll see an HRV for the ventilation and then a separate furnace or other air side system for heating and cooling instead of a water side system for heating and cooling. Okay, so let's look at now some strategies on the heating and cooling side. So first off, minimize your loads, okay? So that you can minimize the required system capacity, in other words, the size of the furnace or the boiler or the air handler. And also, and then reduce the annual operation of that system. Okay, so minimize your loads. How do we do that? Well, better envelope, better windows, you know, smaller building if possible.
Lower setback.
If we're designing a new building, yeah, setbacks, yeah, some controls things we're gonna talk about on Friday, absolutely. Properly size the equipment, so don't oversize or undersize it. If you oversize it, it short cycles. If you undersize it, it runs, you know, full throttle too often and it wears itself out. But also, in either case, they lose some efficiencies. Choose the highest efficiency systems and system components that you can afford. Or if it's existing, you know, try to find ways to upgrade or retrofit it to higher efficiency components. Okay. Take advantage of free heat sources, and I put free in quotation marks here because, you know, nothing's free. But what I mean there is like heat pumps that pull heat from the ground or from the air.
We're gonna discuss that.
Yeah, a little bit, yeah. And then modulate the capacity to match capacity to load, okay? So when I say modulate, I really mean, I'm trying to differentiate from cycling, which for residential systems, cycling has been the norm, on-off. So the furnace kicks on when you need heat, it runs at a full fire until the heating is satisfied and it turns off. Okay. On, off. That's okay.
Once again, that seems, you know, I mean, it seems intuitive.
Yeah.
to the uninitiated.
Yeah, it is. It's a simple way to deal with the situation, and it's okay, especially if you don't oversize or undersize. Okay, and cycling's okay, but even better is to be able to modulate. So a lot of more sophisticated furnaces and
slow,
boilers.
steady.
Well, it can be if you need very little heating, then it fires at a low rate. As the demand for heating increases, the fire rate turns up. So you start opening a gas valve more and introducing more combustion air. You know. If it's not a furnace or a combustion piece of equipment, and so the same thing there would apply to boilers, right? But let's say it's a hot water coil in an air handler, you can have a modulating valve that if you need very little heat, it just cracks the valve, allows a little bit of hot water to flow through the coil. As demand for heat increases, you start opening the valve more, and the valve just sits there and modulates between closed and open to maintain.
But it's more of a constant maintenance rather than a periodic burst.
Yeah, exactly.
Okay.
Analog versus digital, that kind of thing. Even in residential, even a lot of hydronic systems like for radiant floor, they tend to get installed as cycling or binary systems because, modulating valves and modulating dampers and modulating pump speeds and modulating fire rates on combustion equipment is more expensive. It's more complicated, more expensive. It does work better, and it's much more common in the commercial world. But even in a radiant floor heating system in a building, you'll tend to see pumps that you'll either have zone pumps that just cycle on and off, or solenoid zone valves that open close, you cycle open close instead of modulating. But
Doesn't that kind of affect the comfort of it?
it can. And again, that has a lot to do with whether you oversize or undersize things. Sizing is kind of critical with things that just cycle. If you have modulation, the modulation can take care of some. If you've oversized, not so much undersized. Undersizing you can't really help. But if you've oversized the system, the modulation can help with that. If you've oversized the coil in an air handler with a modulating valve, the valve just might never open to 100%. It says, I can make as much heat as we ever need at a 40% open position. That's as far open as I ever go, right? So it can do that. It can take control of that for you. Whereas if it was a binary valve and every time it went full open, okay, you got this big burst of heat and it was oversized, so now you overheat the space and then it shuts immediately.
Yeah.
It short cycles.
And it waits till it gets below comfort level before it starts all over again.
Potentially, yeah. Okay, so try to find ways to have modulating systems. That could be the speeds of fans or pumps. It could be unloading compressors in some kind of refrigerant-based system, or it can be these kind of modulating valves and dampers and things we were just
I
talking
don't know
about.
what that means, unloading compressor.
Yeah, it's just capacity control for the compressor. Think of, I won't get into it too much, but it's comparable to like if you could just vary the speed on the fan instead of, I need air, turn it on. I don't need air, turn it off. Right? Modulate the fan speed. It can be less air, more air. The compressor is the prime mover in a refrigerant-based system. It's like a pump for refrigerant. So you can modulate it instead of just on off. Okay. Again, consider decoupling your heating cooling systems from your ventilation systems. Not necessarily the best thing to do, but at least look at it. Okay. Hydronic systems versus air, much easier generally to provide zone level control. Okay, if you've got a furnace or any kind of ducted air side system, how are you going to say, well, I need heating and therefore air at that bedroom, but I don't want any over in this bedroom? You'd have to have zone dampers all over the place, and then you're getting into like a more complicated air handler system like we see in commercial, like a VAV system or something like that.
Well, then aren't typically those systems set up so that all the dampers are intended to be open? And I mean, somebody told me if you go around and start flipping dampers closed because I don't want my bedrooms heated after all.
In the residential world, those manual dampers, those are balance dampers. And they were, ideally they would have been set one time by somebody to make sure that when that fan moves a total of 2,000 CFM, 40 of it goes to that room, and 60 of it goes to that room, and 100 of it goes to that room. They balance the system. Right. And if you go moving those dampers, you disrupt the balance of the system. Right. What I'm talking about more is motorized dampers that are controlled that you don't tend to see in any residential system usually. Right? This is a commercial world thing that is unlikely to make its way into the residential system.
It turns out the computer room is way too hot.
So close the air off, modulate a damper down, neck it,
right,
close it off, right? But But with residential hydronic systems, we do see where you've got one loop that goes to the radiator in that room, and a different loop that goes to the radiator in that room, and each
It's
loop has
much
its own
easier.
valve or pump,
And
and
it's
so.
much easier to
Yeah,
moderate.
much easier to do that zone level control, to say, I want heat in that zone, but I don't need it in that zone. Okay. And zoning obviously is good, because you could have let's say you've got a guest room
Mhm.
that you don't really need to maintain a guest room at 70 degrees when there's nobody in there, right? Look for heat recovery opportunities. Utilize solar energy by active means. So, for example, solar hot water. In a heating-dominated, mild summer climate like Missoula's, don't provide mechanical cooling if you don't really need it or can avoid it. Right? I mean, it's nice to have. I'm not here to tell anybody what to do, but yeah. But if your priority is to make an energy to minimize your energy footprint.
Mhm.
And you can get away without air conditioning, then get away without air conditioning. Okay. No judgment for people who want to have it, but it's all about individual priorities. But the reason I bring this up, I guess, is because I see a lot of folks. What's happening right now is you see a lot of these scenarios where somebody says, "Well, my priority is energy. I want the minimum energy footprint,
Mhm.
and I understand these heat pumps are the most efficient."
Mhm.
So then, and the heat pumps can be the most efficient way to heat and to cool. But now you put a heat pump in, and because the heat pump can provide heating and cooling, and you didn't have cooling before, you've actually just added a new feature, okay, that costs something. So
Right.
the heat pump is even more efficient if you only use it for heating and don't run it at all in the summer. But
Right.
most people aren't going to do that. They're not going to have a heat pump that can heat or cool, and they just flip the switch to off in the summer when they could have air conditioning. So again, I'm not trying to make judgment, it's just make the decision. If it's really your priority to have the absolute lowest energy footprint you can have, and you put a heat pump in, then if you think you can live without the cooling in the summer, then you turn it off or at least minimize it, only turn it on when it's just bleedingly hot, and, or choose your set points carefully, or have
You just
setbacks and
can't get to a
schedules.
river, one of the rivers
Yeah.
that surround us here.
Yeah, so it's just a consideration. Then, and then some efficient control strategies that we'll talk about on Friday are an important part of this, right?